Welcome everyone, and thank you for attending today's webinar about our new software solution for automating fault location, isolation, and service restoration, or FLISR. My name is Tristan Beaudois. I'm a marketing program manager from Pullman, Washington, and I'll be today's moderator. Before we start, I'd like to bring a few items to your attention. This webinar will be an hour long, including questions at the end of the presentation, and there will be a recording available on our website shortly after. During the webinar, all participants are muted, but if you have any questions, you can submit them in writing using the Q&A tool at the bottom right-hand corner of the application. Our panelists will respond in writing throughout the presentation, and the presenter will also answer questions aloud near the end of the webinar. Any questions that aren't addressed during the live event will be answered afterwards via email. Our presenter today is Brian Fazzari, and we also have software engineer Mike Jones, principal engineer Brent DeSpain, and Senior Engineering Manager David Prestwich joining us today to help answer questions during the presentation. Brian Fazzari is a Senior Engineer and SEL's Distribution Automation Technology owner. He received his bachelor's in electrical engineering from the University of Idaho and joined SEL in 2007. Brian has extensive experience designing, configuring, testing, and commissioning a wide array of utility and industrial automation solutions, and his current focus is on the development of next-generation distribution automation products and solutions. Now, I'll go ahead and pass the microphone to Brian, and we can get started.
All right, thank you very much, Tristan. Okay, so today we're going to be doing a product introduction. So my objective here is to do just a couple slides and then get off the slides and show you the product. So we're going to do a lot of demonstration today, and hopefully this shows, hopefully by the end of this, you feel that you've seen the entire product from beginning to end. That's the goal. So can we do this in 1 hour? So first, let's talk about automation systems in general. There are a lot of ways you can do automation. What is automation? You're teaching a computer to do a task that today or yesterday was a human task. So in a way, there's kind of an analogy here. You're teaching something to do your job, or you're teaching someone to do someone else's job. The point is, we're going to instruct the machine how to accomplish a task. What do you do to do that? What does that take? First, you have to give it instructions. These could be rules, they could be algorithms. These are settings, right? This is the red box on the upper left-hand corner of the slide here. You're going to give it a set of rules that tells it how to behave and what to do. Now, almost always, an automation platform, in order to accomplish a task, needs data. So you need to configure the automation platform with settings so it knows how to behave, and you need to configure an automation platform with data settings. So how does it acquire that data? What format does that data come in on? Is it an analog? Is it a binary? Is it a control? Is it something else? Does it need to be scaled? Does it need to be inverted? So I can draw an easy picture here on the slide, but this gets complex pretty fast. There's a lot of variety out there. So when you're designing a product or working with a solution that is designed to do a technically complex task like automation platforms tend to do, the challenge is, how can we keep that simple? Okay, so you have an automation platform. It's consuming data. It's sending controls. It has settings. You're pretty sure you trust it. It's doing the right thing. How do you know that it's doing the right thing? So there are 3 parts to that. The first is, can I test it? And can I test it without significantly modifying the thing that I'm testing? So the algorithm running on that automation platform ideally gives you a way to test it, to exercise it, to learn how it behaves to the point where you can predict what it will do, and you're right. You're always right, or at least almost always right. That implies the existence of some kind of user interface. So something that can tell you, what is that automation platform seeing with incoming data, and what's it doing in reaction to that data? Is it issuing controls? Is it analyzing that data and spitting out information? What's it doing? Now, that's while you're looking at it. For the purposes of FLISR and many other types of automation systems, the chances that you will be looking at the user interface when it needs to take action is pretty low, unless you're commissioning. If this is a live system, It tends to happen when you're not looking. So it's very, very important that you be able to do what's often called post-mortem analysis. The platform is operated, and you need to go back and look and see why it did what it did, especially if what you predicted it to do is not what it did. It should be able to explain itself using reports. So settings, data, as simple as possible, teaching the automation platform how to do something with information and how to get that information, and then be able to continuously interact with that platform by testing continuously, interacting with in real time with the user interface, and reviewing and auditing using reports. All of these are super critical for an automation platform, especially one that is a control system like FLISR. It's allowed to open and close devices on the distribution system. You need to be able to trust it. So let's talk a little bit more about that. Anytime you interact with a machine, you are working generally through a human-to-machine interface, and you can categorize that as a user experience. What is it like to teach this machine how to do this job? And you could put it on a scale like this. This always reminds me, every time I put this slide in front of me, I think of Star Trek IV, The Voyage Home. So for those of you who've seen that, there's a famous scene in there where Scotty attempts to speak to a computer. And it's an early generation Mac. It's a keyboard, a black and white screen, I think it's black and white, and a mouse. And he tries to talk to it, and people look at him like he's nuts. This is a perfect example of what we're talking about here. If you're going to teach a machine how to do a task, what does that machine require of you in order to teach it? So on the far end of the machine side, we're talking about a programming language. So generally, we're not writing assembly these days, although I've done it before. Not a huge fan, but let's assume we're not writing assembly language, and we have access to things like pointers, classes, functions, methods, and arrays. These are typical tools you get in your toolkit when you select a programming language. The purpose of that programming language is to teach a computer how to do a job. Close to that is text-based programming. So it is possible to be given a set of function blocks or kind of pre-configured functionality that don't require you to actually use pointers and access memory and do garbage collection and all the stuff you might have to do as kind of a software developer, but you still have to write code and you still have to understand all the intricacies of that code as you write it. So let's keep moving here. As you get closer to how a human might communicate, so think about you're teaching something how to do a task. What if it were a coworker or a colleague? Well, clearly you don't teach them using text-based programming. You may use a block diagram or a table of rules. So we're getting closer to how a human would intuitively teach a task or delegate a responsibility. But we could go even further towards that voyage home scene. What if I could draw my settings or what I want the rules to be on a whiteboard, or have it just look at a drawing and understand it, or even better, use natural spoken language or written language. Now, we're not quite there yet. That last bullet is, I look forward to playing with that in the future. But what we're really going for is almost always when you're teaching another human being how to do something, if it's a graphical concept like FLISR is, the automation system needs to understand the topology of the theater, we almost always end up at a whiteboard with a marker. Hopefully that marker is fresh and you can draw a really crisp picture that lets your colleague quickly understand what we're talking about. Who's upline of who's downline of who, where are the PTs, where are the critical loads. That's a graphical concept. And so being able to abstract that out of a text-based programming environment and just draw a picture was our ultimate objective here. If you don't trust an automation solution, it doesn't matter how slick and polished and chromed it is, you'll eventually turn it off. The reason for that is because the whole purpose of introducing automation into our lives as engineers or technicians or any technically minded people is to make our life easier. And if you can't trust that that solution is going to do its job as you would do or better, you're going to end up turning it off, either because it misoperates or because you just don't understand what it might do. You can't predict it. It's not making your life easier. So this is always the big challenge when you try to productize an automation solution. So typical characteristics of a trustworthy solution would be one that is simple. Now, is there any such thing as a simple software-based product? You could argue, no, there's complex code usually under the hood that's doing some pretty amazing things. But does it come across as complex and difficult for the user? If so, it's hard to trust such a solution. Will it do the right thing, or did you tweak the wrong settings somehow and you're just not sure? Does it make its operations visible to you? Does it give you lots of easy ways to check in on it and see that it's doing the right thing, it's seeing the right thing, it's armed, it's operational, it's in the right mode? Is it easy to figure that out? Is it testable? Can you, at the drop of a hat, decide, I'm going to run some tests on this system? Does that system give you an easy way to run those tests? If so, it's a lot easier to stay comfortable with that system. So I can give you some personal examples. When you commission an automation system, hopefully you don't have to touch it for a while. Eventually you will. You'll have to change a setting. You'll have to add a new recloser, change the way PTs are hung, something will change. It might have been 6 months since you looked at those settings. Do you remember exactly how they work? If you're not using it all the time, memory fades, right? This happens for everyone. If you aren't using it all the time, memory fades. So making it possible to pick up that solution, test it, exercise it, reorient yourself, and get familiar with it is really critical for a control system. Is it modular? Modular is very helpful because it allows you to take a piece and study and understand that piece of the solution without having to keep the rest of it in your mind. This is why we like building with Legos. I'm sure there are other reasons. We could debate that after I'm not being recorded anymore. But what's fun about Legos is you can construct a little piece of a solution and see it all come together and have some understanding of how that all works in a modular piece-by-piece way. It also makes it easier to maintain, so modular and maintainable go together. It is easier to maintain something if you can just pull the piece that needs work on it and put it back. So an analogy of this would be an engine. There are lots of other analogies. I should not have to understand the entirety of every component of an engine in order to change the oil or change the spark plugs. There's a specific process I can follow to work on a specific piece, a certain part of how that system, that complex system works without having to know what everything else does. That's a better design. And automation systems can be designed the same way. So let's get to FLISR specifically. What is it? FLISR stands for Fault Location, Isolation, and Service Restoration, as Tristan mentioned in his introduction. What is that? Well, so when a fault occurs on a distribution system, the first thing that should happen is a protective device should detect it and react to it. So fault occurs, protective relay should trip. That has nothing to do with FLISR. So in the bar along the bottom, that whole red protect region, that's the protective relay. FLISR does nothing here. Most faults are temporary. They resolve either by the passage of time, brief amount of time, or by reclosing. A reclosing device is an incredible reliability improvement to the distribution system. So if a fault occurs here on this system, a breaker or recloser should trip and immediately reclose. Depending on the circuit or the utility or the time of year, the number of times that device attempts to reclose may be once, twice, 3 times. Eventually, though, if that fault just is there every time we re-energize the line, the recloser gives up. Right? It reaches its shot count. It goes into what's called lockout. Lockout, we can monitor remotely, and we can see when lockout is asserted that recloser is open and is no longer going to attempt to reclose on its own. that fault is now an outage. It is permanent, a permanent outage. Once that happens, so once lockout comes in, now FLISR gets to do something. So there's a permanent outage on the circuit. The recloser is not going to deal with it. Now our objective is to make that outage as small as we can and make it as short as we can. So let's go through an example. So here you have a distribution feeder, lots of reclosers, 6 of them, with a line tap, and a breaker on the left. The high side of the breaker is to the left side of the breaker. So there's a source of energy flowing from left to right in this picture. So what we're going to do here is just demonstrate what this feeder would experience if FLISR did not exist. So what I'm going to do here is apply a fault near this line tap. So when that happens, there's an overcurrent fault, recloser 1 will see it, breaker 1 will see it, and the recloser will open. Again, this would indicate, or this would simulate a reclosing shot, right? The recloser will open and then it will close, and then it may open again, and then it will close. Eventually, if the fault is permanent, that recloser will lock out. And you can see I'm just driving this using the integrated simulator in FLISR. So we're going to be in the product for the rest of this presentation. So what you have here now is an outage, right? Everything downline of recloser 1 is experiencing an outage. The green boxes are PTs. PTs telling you that the voltage is dead. The line is de-energized downline of that recloser. So now we're going to arm FLISR. We're going to do the exact same thing again. There's a fault on the line. The recloser trips, and FLISR does nothing. There's no lockout. Most faults are temporary. So let FLISR sleep until the recloser locks out. As soon as the recloser locks out, FLISR should detect an event. It should know there's a fault on the line. There's a lockout accompanied by a fault indication from recloser 1. So now its job is the first 2 letters of its acronym, fault location. Locate that fault, isolate it, which you're seeing now, and restore, which you just saw. So that is the difference. We're able to make that outage as small as we can by isolating it, opening recloser 2 and 4, and shrinking what we call the fault boundary, the boundary of devices upline and downline. Once we do that, we're able to restore all load that's not unfortunate enough to be in the same zone as the fault using adjacent circuits. So you have feeder 2 and feeder 3 over on the right that were available to assist. Now, some of you may be thinking, man, that's not, when I think about it in terms of rules, that's not too difficult to write. I could just write that in code. True, you probably could, but there are a lot of things to take into account here. There are a lot of gotchas, corner cases, and things to consider. So let's do a couple more. So this is the same circuit. I'm going to place a fault in the exact same spot. You're going to see that recloser 1 and breaker 1 both see it. Now, if they are set correctly, they should coordinate. Recloser 1 will lock out. But what if they aren't? What if the breaker locks out? Now you have a choice. If you had written some sort of script, you may find that the fault is in between breaker 1 and recloser 1, which is wrong. It's downline of recloser 1. So FLISR's job is to recognize that that is a miscoordination, and it can correct that miscoordination automatically. The fault is in the same spot as it was in the last example. Now, I would like to return my circuit to normal. So I have this outage. I've gone out, I've repaired the fault, and I would like the circuit to go back to the way it was before the fault actually occurred. Now, in this case, I am having FLISR close the recloser for me. Most procedures you would close that recloser manually, make sure that it held, that the fault was truly repaired, and then optionally allow FLISR to return the rest of the circuit to normal. that would work as well. Okay, so we've issued a return to normal control that's resulted in a sequence of controls being sent to reclosers that returns the circuit to normal. Let's do another example. So this is going to be another miscoordination, but in this case, both protective devices lock out. So breaker 1 locks out, recloser 1 locks out. What do? This is where it's important to follow the fault indications, regardless of who locks out. So again, you're going to see a very similar reaction here. We close the breaker back in, but we do not issue an open control to recloser 1 because it's already open. So the result is the same. We minimize the impact of the outage. We restore as much load as we can. Let's do another example here. Feeder 3 is heavily loaded. In all of these examples so far, feeder 3 picks up 20 amps of load. You can see 10 amps and 10 amps across 2 zones, and you can see that R4 is feeding it right now, 20 amps. So what we've done is we've told FLISR, hey, feeder 3 can only give you 10 amps. What does it do? It needs to be able to make the right decision on the fly, or it will overload something. So same situation here, recloser 1 locks out. FLISR will isolate the fault, and it will sectionalize the outage territory. So the area between R4 and R6 is too big for feeder 3. So we open R5, and we leave the area between R4 and R5 de-energized due to a capacity limit. We're unable to pick up everything because feeder 3 is heavily loaded. If feeder 3 had like a hotline tag or a supervisory cutout applied, it wouldn't have told us it could give us 10 amps. It would have told us it can give us 0 amps. Right? There's work happening over there. We don't touch feeder 3 when work is happening. So you would see a similar behavior, except R6 wouldn't have closed at all. So let's build some of these things. I started off with, we're in the simulator, the circuit's already built. What is this like to build? Now, depending on what FLISR solution you have experience with or have been shown, this can be done many different ways. It can be derived from a GIS model. It can be written in code. It can be written in rules, in a tabular or Excel style spreadsheet format. There are a lot of ways you can do this. What we attempted to do is create that whiteboard type environment so that that is literally all you need to do FLISR. So let's see how that works. So I'm going to create a new feeder. I call it feeder 3, and there's only one setting there, right? Do we want to detect miscoordination or leave it alone? And there are a couple other threshold type settings in there that I can go into details on if any of you would like to contact me. I'm happy to dig into this however deeply you'd like. But what I'm doing now is I have this blank virtual whiteboard. We call it a canvas, a feeder canvas. And what I'm doing is I'm dragging breakers and now a recloser onto the screen and connecting them as they are connected in the real world. This is what teaches FLISR how to contextualize the data that it gets when it talks to breaker 3 or recloser 9. So I've added a line tap. I'm going to add a couple more reclosers here, and I'm going to hook them up. Now, an important thing to note here is there aren't a whole lot of restrictions here on the screen about where I can place these reclosers. I'm kind of putting them wherever I want. There's a little bit of snapping mechanism there just to make it easier to line stuff up, mostly because many of us started to lose our minds when we didn't have a tool like that. You got to get them lined up or it starts to bother you, believe me. So recloser 9 is now on the screen, and I'm going to tell it that PT set 1, so 3-phase voltage measurement, faces the local source, and it tells me immediately if I make a mistake here. That was a big objective of ours. There is no save button, and there's continuous validation. It should tell you immediately if there's a setting that doesn't make sense, either for FLISR or for the physical world as a whole. You can't have a voltage measurement measuring 2 points on each side of the switch. Okay, so now I've quickly set up PT locations on each side of these switches. I'm just showing you several different ways to do it here. You can either interact directly with the device, or there are several ways to do it. And now I'm adding a connection to an adjacent circuit, another feeder. You can call these whatever you want. You will develop a routine that makes sense for you or for your organization. I like to name them after the device they're closest to. So @recloser 5 is right next to recloser 5, and @recloser 7 is right next to recloser 7. This will make more sense in a minute. I'll show you how we use these. You can see for now that they are unassigned. I'm not connecting them to anything. I'm just leaving them there. Okay, so we've set up a relatively simple feeder here, single line tap, 3 reclosers and a breaker. I haven't set up DNP. I haven't connected my adjacent feeders to anything, but I'd like to see how this works. FLISR should have enough information here to work. So when I click that simulation button, it's a single button, I should be able to, in a browser window here, which you can see, I'm just using, in this case, Google Chrome. In a browser window, I get operational FLISR, not modified in any way, but dropped into a secure sandbox. And it shares that sandbox with a simulation that allows me to open and close devices and place faults. And FLISR thinks it's talking to the real world when we're doing this. So if I click on this line segment between breaker 3 and recloser 9, I can apply a fault that results in a lockout. And you can see that breaker 3 locks out all by itself. That's the simulator simulating what the real world would do. FLISR is reacting to it. It doesn't know that this isn't real. It's sending controls that would go out over DNP if we were not in a simulated environment. And you can see that recloser 9 open, recloser 5 closed. So we used that @rec5 connection to an adjacent feeder to restore. The simulator assumes if you're putting a connection there that there's a feeder on the other side of it, and it will simulate that for you. So now we're issuing a return to normal, and it returns the circuit to normal. What's so cool about this is if you have a circuit you want to evaluate for FLISR, you can either think through it using a whiteboard or diagram, or you can just draw it in the product, throw it into the simulator, and start throwing faults at it and see what it would do. So again, I can set a capacity limit here. So at rec 5, whatever feeder is on the other side of that, only has 10 amps to give me due to heavy loading. And we should be able to quickly see what effect that has on FLISR. So fault is in the same place, but there's 30 amps to pick up right there, and it won't be able to do that. So it'll go to the next available source, which is that adjacent one at the bottom. It's called @rec 7. So you can see rec 7 was closed instead of rec 5. The only thing I changed was the availability of those adjacent circuits. Now here's the reporting part that we talked about on the first slide. If I wasn't watching, I should be able to come in and see what it saw and what it did. So where did the issue occur? What was the issue, so fault in this case? When did it happen? What did my feeder look like at the moment lockout occurred? And what did my feeder look like afterwards? So an important note here is it's drawing in the report here exactly what I drew in my settings. So if I didn't care about things being lined up, they wouldn't be lined up in here either. You also get a table that shows you what happened. So 3-phase loading pre-fault, status before and after. We've added a lot of tool tips and data here. The objective is you should be able to make intuitive sense of what this control system saw and did. So what did it do to isolate? So it opened recloser 9, and it ensured that breaker 3 and 5 were already open. What did it do to restore? It talked to the neighbor across that @rec 7 connection, ensured that there was enough margin, and agreed to close recloser 7. And that's the next step, closing recloser 7 completed at 107. It will tell you optimization order, which for now is fixed. We have some interesting ideas about more options to adjust that in the future, but for now, you're picking the one that restores the most load and switches the least amount of things. So here's the other one that we ran, which was that capacity limit situation. So you can see here, sorry, wrong report. I want to see the capacity limit one. So we're going to go back to that what is FLISR thing that we were running before. This is the circuit we ran first. You got a report for each of these as well. The feeder, I literally named the feeder what is FLISR so that it looked like my slide title, but that was the name of the feeder. And this is a case where you had a capacity limit. You weren't able to pick up all zones. So it'll tell you at the bottom, this zone bounded by the following devices could not be restored. The neighbor didn't have enough margin. So we can walk through exactly what it did to restore and isolate, where was the fault boundary, and if there were a problem, if it wasn't able to do everything you thought it should be able to do, it will explain itself, which is pretty helpful if you weren't watching it at that time. Now, when you close that simulation, I just closed that tab, the simulator gets deleted. It's like it never happened. The reports will stay, but the actual simulation gets deconstructed and removed. If I want to run a simulation again, I can click that simulate button again and I will get a brand new one. In fact, you can run multiple simulators at the same time on the same circuit if you want to, or the same circuit with simple modifications. So let's add to this configuration. So far, we've been sticking with one feeder. Let's do multiple feeders. So we're going to add feeder 1 here. And you can see it shows up in the list on the left. These are drafts. And I'm going to draw a new breaker. This will be breaker 1 because it's feeder 1. Makes sense. We'll add a recloser. Another recloser. Another recloser. I can multi-select. I can drag grouped things around. I can drop stuff right on top of a line, and it's smart enough to connect it to that line. I'm going to add a connection to a neighboring circuit right there in the breaker zone and downline of recloser 6. And again, I'm naming it based on the closest upline device. We're going to add another circuit, feeder 2. So we now have feeder 1, 2, and 3. And just real quick, I'm going to configure feeder 2. You can see I'm using a different mechanism for inserting things into the canvas. So dragging and dropping from the palette is intuitive. It's something people generally try first, and so it should work. However, it does require you to move the mouse back and forth. And if we're looking for efficiency, technically being able to keep your mouse in the same spot is more efficient. So you can just click on the spot where you want the next object connected and insert it. And that's what I'm doing here. So what I want to do is connect this neighboring feeder connection to this one over here. So what I'm going to do is glue them together or link them. So I'm going to connect this feeder 2 at rec 1 to its contemporary on the other circuit, which is called at breaker 1. It now knows they're connected and I can browse back and forth. So let's do this again. So we're going to add a connection called at rec 3, and I know that that is connected to feeder 3 at rec 5. Rec 5 is the open point. Now we've connected these two together and I can browse back and forth between the two. FLISR knows that there's an electrical connection at that point now. Okay, I just deleted all my work, which hurts me a little bit, but I want to show you how you can import and export settings. So previous to these recordings, I configured all of these circuits and exported them, and I saved them on my hard drive. So let's grab that configuration again. So I have a 4-feeder configuration. I'd like to open it. And that's all it takes. I have 4 feeders imported, already laid out. All the settings are there. It's ready to go. These feeders are even linked together. I see that the linkages are there. I can browse from feeder to feeder to feeder in this way on the canvas if I want to. It's all there. So that's pretty convenient. You can import and export from DMS Designer, which is what this application is called, and keep track of your settings very easily that way, or move them from Blueframe to Blueframe. So many of you have probably noticed there is what looks like an error symbol associated with each of these switching devices. What is that? So there's a tooltip. There's also a validation window down here. And what it's complaining about is that no communications are configured for this device. So we go to another application called Protocol Services. Protocol Services is where you configure DNP in Blueframe. So what I'm going to do is make a new DNP client connection called Rec2 or Recloser 2. I would fill out my IP address and DNP settings here. I would configure my binary outputs and analog inputs, all the stuff you would expect for DNP in these tabs. But I'm not going to do that just yet. I'm going to go back to DMS Designer and let's take a look at Rec2. So let's go find it. There it is. And you can see that Rec2 doesn't have an error anymore. DMS Designer has located a DNP connection called Rec2, and it's no longer throwing an error. Now, there are some warnings because clearly that Rec2 connection that I just made has no data in it. So it finds the Rec2 connection and it starts looking for things like three-phase current, voltages, breaker status, lockout, fault, open and close command, and it doesn't find any of them because we haven't created any of those in the DNP connection. But it does tell you exactly what it's looking for, and you can export that as a report. So you can export it as a CSV or as an Excel spreadsheet to make it easy to keep track of what FLISR is looking for. Okay, so let's hook some of these up. So I have Recloser 2. It's looking for these pieces of information. How do we connect this information? How do we add, for example, three-phase current to a DNP connection and connect it to FLISR so that FLISR can use it? So I'm going to open Protocol Services on another tab. Now let's just keep this list open here. There it is. So we're looking for three-phase current, for example. It's at the top of the list, so we'll do those first. So I'm going to go over to the Protocol Services tab, locate Recloser 2, and we're going to add some analog inputs. I'm going to add 3 points. I'm going to call them IA, IB, and IC, and I'm going to save these settings. So there's, we'll add 52A3P as well. So this is three-phase breaker status. So all I'm going to do is save this DNP connection settings and go back to DMS Designer. And you can see that IA, B, and C is gone and 52A3P is gone. DMS Designer every 5 seconds checks for data. And if it finds it, it will hook itself up. So there is no wiring of data to be done here. Everything is done by name. If you name it what DMS Designer expects, FLISR can use it, and it will use it automatically. So you can see things disappearing from this table as it checks for information. Okay, I have now deleted the DNP configuration completely. So Protocol Services is empty again. You can see Rec2 is complaining about not being able to find DNP again because we deleted Rec2's DNP connection. It doesn't let you deploy anything if there's not a DNP connection associated with these devices, which makes sense. You can misoperate if you don't have a clear picture of the system. What I want to demonstrate here is just like you can import and export your DMS Designer configuration, you can import and export DNP settings as well, and that's what we're doing here. So what I'm going to do is import DNP settings for all 4 feeders worth of breakers and reclosers. And give that just a second. So what's happening in the background here is a connection is being created and set up for every client that was in that import, and there were a bunch of them. There we go. So we have all these reclosers and 2 substation connections, 2 RTU connections. So you can see their IP address settings, the right server IP port, everything is set up correctly. All my data is here. And if I go back to DMS Designer now, you will see that all of the errors are gone. And look at that deploy feeder button. It is now clickable. It's not grayed out and disabled anymore. So every single feeder looks to be happy. There's nothing in the validation window, 0 errors, 0 warnings, 0 info, and I can deploy this feeder. That feeder is now operational. It's not armed. It won't do anything until you arm it. But I can deploy that feeder, and it's smart enough to tell me, hey, you just deployed a feeder that has neighboring feeder connections that are not deployed. So let's deploy the rest of these. And you can see those warnings update as we deploy different feeders, and once we've deployed all 4, all those warnings go away. So now I am not able to edit these settings anymore. Everything's grayed out. I can't edit anything. But if I go to the FLISR application, I see my 4 feeders. Here they are. Now, we don't have any DNP connections going right now, so it's telling you. I have no idea what the breaker status is of any of these devices, but they're all here. And here's the data I'm looking for. And I'm not seeing most of it because we haven't started DNP. So let's go back to protocol services and start all these DNP connections. So I can deploy 1. I'll deploy Rec2 in this case. That will start essentially the DNP driver. DNP will start for Rec2, and you can see immediately it locates DNP data. So we see voltage, we see current, and I can just bulk select all of them here and deploy them all. So what you're going to see here, pretty interesting, you'll see a little green dot telling you that communications are good and online, show up next to all except recloser 13 through 18. The reason for that is because there is no DNP connection on the other end for these guys. There is no Rec 13 out in the field. And so you can see at a glance that there is a communications issue with those reclosers. Now, Rec 13 through 18, I didn't use in my FLISR configuration, so this doesn't worry me. So now I can start arming these circuits, and we're following the same paradigm here. You have a little dot next to each feeder in the list over there, and that dot will turn green if it's armed. You'll see a little lightning bolt if there's a fault. If there's an issue with it, you'll see that warning symbol that you saw briefly a second ago. So now I can create a permanent fault. I'm using an RTAC to generate all this DNP data, but this FLISR system is armed. It's going to send DNP controls. So we're going to put a permanent fault on feeder 1. All of these circuits are armed, so how does this work? So now when a fault occurs on feeder 1, it talks to feeder 4 and feeder 2 for real. So you can see it seeing lockout. It's issuing an open control to recloser 4, a closed control to recloser 6. And this is a little slower looking because now we're using real DNP. We have to wait for the DNP pull interval to bring us that recloser 6 status. We're waiting for it here. So you can see it's just sitting there patiently reconfiguring, waiting for recloser 6 to close. Okay, so that is deployment. We're running a little bit short on time here, so I'm going to, let's see, I would like to show you how to edit a circuit while deployed. So let's say recloser 4 is having an issue, and I would like FLISR to just work around it. So you have options there. You can mark it as out of service closed or open. You can tell FLISR not to issue any controls to it. And you do that right here in the user interface, or you can do that by issuing a DNT command to FLISR. Or let's say Recloser 4 is just, it's gone. We took it down and we moved it somewhere else. I would like to be able to remove Recloser 4 from my FLISR system. How do I do that? So I'm going to edit feeder 1 while deployed, and I'm going to delete Recloser 4. Okay, it's like it never happened. Recloser 4 is no longer there. Now, FLISR is still running, and it's running with Recloser 4 until I apply these changes. So I'm going to go ahead and apply these changes, which overwrites feeder 1. And now I'm going to go back to FLISR, and let's see what we've got. So we now have feeder 1 with no Recloser 4 disarmed. So I can come in here, arm it, throw the exact same fault at it again, and it'll work. It will not try to operate Recloser 4 because Recloser 4 is no longer part of the FLISR settings. So there's that fault again, downline of Recloser 2, and almost immediately reconfiguration is complete because there's nothing FLISR can do here. There is no Rec 4 to open. And you can see I get a report for each one of these. This is very short because there's nothing we could do, but we did recognize that there's a fault downline of Recloser 2, and there was no action we could have taken. So it generates a report, and it tells you what it checked, but no action was taken in this case. Okay, so now I want to show you briefly, very briefly, Blueframe. So all of this is running on an SEL created Linux-based operating system called Blueframe. And what you see here is the portal or the application launcher. Any installed applications you have on Blueframe are here. Blueframe gives you some core capabilities. The ability to keep it secure and update it is built in. So for any of you that have sent firmware updates to an RTAC through its web interface should feel right at home here. SEL does issue regular updates for Blueframe that address security issues, if any, and add features. We can also issue updates, feature enhancements, fixes, anything by package. So here you can see that FLISR and DMS Designer are separate. Connection Services is its own application. So being able to upload an update that targets the specific application and doesn't reboot the whole box is now possible on Blueframe. It also gives you the ability to manage users and roles. You can interface it with an LDAP server if you'd like, and there are a lot of different permissions options that you can assign for any given role or user. So the objective here is create a Linux-based operating system that is easy to deploy in an OT environment and lets you do things like FLISR without having to keep track of all of your Linux-based dependencies and all the other stuff you might have to do if you're responsible for an operating system in that OT environment. Okay, so I could talk about this for a long time still, but I should stop because it is 12:48 here in Boise. And if any of you have any questions, I would love to answer them. Thank you very much.
Thanks, Brian. As you mentioned, we've arrived at the Q&A portion of the event now. Just a reminder, you can submit your questions in writing to all panelists with the Q&A tool at the bottom right-hand corner of the application. And I'll go ahead and pass it over to David Presswich, and he'll be leading the live Q&A with Brian.
Great. Thanks, Tristan, and thanks, Brian. Brian, we've and everybody that's been listening in and answering or asking questions, we really appreciate them all. It makes for an exciting hour. We're obviously not going to probably be able to answer all of the questions that have been text, but just as a reminder, we'll still respond back to those after the seminar. So Brian, I'm going to hit you with probably 3 or 4 pretty rapid fire ones that have been kind of common across the questions. One of which was you used the example of an overhead feeder. Could you maybe just at least talk about if we also support the underground side as well?
Yeah, that's a great question. So You're right. Most of my examples were all reclosers, right? I didn't use any switches. There is a switch component in that palette, and so we absolutely support underground distribution. The way you would do that is you would model a switch per, usually source way. We're talking to the source way. So you'd have switch modeling one source way, another switch modeling the other source way, and then you can use a label or a box to indicate which pad those switches are on, but we can absolutely do that. We have some enhancements coming up around underground behaviors as well. We'd like to add some cool stuff there that more completely clears the vault when a fault happens on the bus or on one of the loadways, just to make it easier to get in there and resolve the issue. So if you're curious about any of that stuff, please feel free to reach out to me.
Thanks, Brian. And then two other questions, or two, not really a two-part, but two independent questions I think you can answer at the same time. One was, what applications are required? Do we need to install any applications on my desktop to do some of this designing? And then the second one, which was common, was you used the example of DMP as a protocol. And so other protocol requests, the SEL protocol, for example, just if you can maybe talk a little bit about the plans for supporting additional protocols with Blueframe and DMS. So sorry, two questions. One was
Yeah, no problem.
Okay.
Okay, so the first question was, what software do I need to install on my desktop in order to do this? Everything you just saw was a recording of me using DMS. So all of those usages were me using the software through Google Chrome. And this is one of my favorite things about it. You do not need to install anything on your computer other than a Chromium-based web browser. So Google Chrome and Microsoft Edge we use frequently. They both work great. And so all you need is a computer with a web browser, a modern web browser, and access to the box. So you type in the IP address or the DNS name of the box, however it's configured on your network, and you access that box directly. What's great about that is the box immediately knows your settings, so I don't have to download settings to it. You're making changes right there on the box, but with a clear demarc line between what's a draft and what's deployed and what's simulated. And you're able to do this really cool graphical configuration right there in the web browser. If any of you saw at any of the conferences this year, we were actually doing simulation using a touch screen, and there's no reason you can't do that as well. We do it all the time. Okay, so protocols. DNP is the first protocol released on Blueframe in protocol services, and what protocols we add next is a very popular conversation at SEL here in R&D right now. SEL protocol has come up, Modbus has come up, many others have come up. 61850 comes up frequently, 6870, 104 comes up, and so any feedback anyone has as far as what they would like to see next, please reach out to us and let us know. We're working on that right now.
Okay, thank you. Another question, as you were showing the set values on the individual reclosers, was, how integrated is this with actually being able to deploy or work with actual recloser settings? And is there plans to integrate more with the actual relay settings, Brian?
Okay, so that's an interesting discussion. So I'd be happy to discuss that further as well. But usually the way it has gone historically is FLISR does not modify relay settings, but it does often have to change the behavior of the recloser based on some reconfiguration that it's done. So a real common one is, if this recloser, pick a recloser in your mind, is fed from its normal source, make sure it is in protected settings group 1. If it's fed from this alternate source, put it in settings group 2. Or if this device is more than 2 closed devices away from the breaker, put it in switch mode. Or if I receive a fire mode signal from SCADA, put it in settings group 6, which would be, an extra twitchy, less reclose shots kind of behavior for the recloser. So that typically is the kind of interaction that we have between an automation system like FLISR and the field. We're not modifying relay settings directly, but we are changing settings groups, which has the net effect of changing the behavior of the device. That is not something FLISR has right now, but it is something we're adding in the next year.
Good. Thanks, thanks, Brian. Another question is, how does FLISR behave in relation to COM failures? So if there's a communications failures that occurs, you know, how does FLISR scheme automatically attempt to basically, you know, isolate or restore, for example?
Right. Okay. So the safest thing you can do in the event of a COM failure is to disarm FLISR on that feeder until that COM failure resolves. Now, there may be some people listening thinking, oh man, I really need it not to do that. So hear me out here. So if you have a COM failure with a recloser or switch or even a breaker on a feeder that FLISR is operating on, the safest thing to do is block on just that feeder. Now, other feeders can stay armed and operational, and they can work with each other and work. But we disarm or self-automatically block on that feeder as long as communications are gone. That's how it is right now. Mitigation steps would be you can go into FLISR or send it to DNP control saying, hey, treat that device as out of service closed or out of service open, at which point FLISR will unblock itself and will be perfectly happy to treat that device as a bump in the wire or as an unresolvable air gap, and it'll work around it. We have been asked by multiple people to add a setting to FLISR that is, if you lose comms with a device, treat it as if it were in last known state. And that's something we're looking very closely at. That's something we will probably add. The reason we're taking such a careful look at it is, what if a hotline tag was applied on that device and then I lost comms with it? Do I stay blocked? Do I rearm? Is there a way to mitigate that? And how do we make sure that we do that in a safe way? So there are some corner cases, safety related, that we're still working through, but we're looking at that closely as well.
Great, thanks, Brian. We're kind of sifting through a number of these, and we continue to encourage everybody who's participating to keep sending in those questions. I think maybe a good one would be, because we've kind of got this question a few times from a couple of different angles, referencing how FLISR ensures that the voltage limits are respected, you know, after any kind of self-healing. Does that, let me know if that's making sense, that question there, Brian. I can try to clarify.
Yeah. No, it does. So when you have an automation system like FLISR out there, its job is to lengthen feeders in order to pick up load that would otherwise be left de-energized after a fault. Those feeders can get relatively long, especially if the fault was in the breaker zone or was on the high side of the breaker, you know, in the substation somewhere. So the question, the way I'm interpreting that question is, the longer a feeder gets, the lower voltage at the end of that feeder becomes. Now, you could do something like line drop compensation in a 2431 that would help with that. But usually you want your FLISR system, if you have a voltage concern, to not restore if the voltage is going to be unacceptably low. As of right now, FLISR does not look at voltage at all. What we're looking at is, should it just not restore if the voltage will be unacceptably low, or do we need to add an integration mechanism whereby it can ask for the voltage to be raised, or it can disable a CVR scheme and wait until it gets a signal from that scheme saying, yeah, it's off, we're good, and then it can proceed. That's what we're looking at right now. So FLISR today is not looking at voltages at all, but in the near future it will.
Thanks, Brian. Okay, last question, and again, we'll get back to everybody as quickly as we can. You referenced the DMS designer and FLISR running on Blueframe and quickly ran over that. I will let everybody know that we have had a couple of previous webinars that have included and talked about Blueframe and gone into a little bit more detail, so I encourage you to take a look at those. But Brian, the broad question, and this will be the last one, is kind of where exactly does FLISR, this FLISR application and Blueframe, where would you expect it to be running from a customer standpoint?
Historically speaking, when we have done FLISR on what's been the RTAC before Blueframe, there's been kind of a 50-50 split between utilities that want to put this type of system right there next to SCADA or in a communications front end somewhere, or distribute it out into the substations. We designed FLISR partially feeder by feeder for that reason. So right now, FLISR needs to go on one box, one Blueframe box. But a feature that we're working on this year is adding the ability to have those feeders talk to each other over an external network. So if you can talk substation to substation, there's no reason you can't model 4 feeders on a Blueframe box in one substation and have it communicate over a network to its adjacent feeders running on another Blueframe box at another substation. So if you look through SEL literature for FLISR, or for DMS, Distribution Management System, which is what this suite is, we'll be building it out to be more DMS-like as we go, it will say coming soon for that regional type distribution. So ultimately, you should be able to decide what works best for your organization, whether you're putting it next to SCADA or next to a communications front end, or whether you're distributing out into the substation. It should not matter. You'll configure FLISR the same way.
All right, thanks, Brian. I think that's it that we'll cover here. And again, we'll get those answers back to you as quick as we can. But thank you, Brian, for the presentation. Great job, and thank you, everyone, for bringing in the questions.
Thanks, everyone.
Thanks, Brian. Thanks, David. As you mentioned, we're at the end of the hour, but again, if your question wasn't answered, we'll reach out to you via email soon afterwards, and this recording will be available on our website soon afterwards as well. Also, if you'd like to learn more about the topic in general, you can visit our website. And on our homepage right now, you should see a link to more information about this FLISR on Blueframe solution. So we hope everyone enjoyed today's event, and we look forward to seeing you all in future SEL webinars. Have a great day.